Number 24 in 5.3 is asking you to take the antiderivative here of a fractional function here with variables on both the top and the bottom. 12 minus z in your numerator and the square root of z in your denominator, all taken with respect to z. Now, the easy mistake to make right here is to think that you can simply reverse the process of differentiation here in order to come up with this antiderivative. One of the things I'll talk about a lot with you guys is that if we were just trying to take the derivative of this function right here, what rule would that one require? That derivative would need the quotient rule because we have a function that's written here as a quotient with variables on both the top and the bottom. And the quotient rule and the product rule, everybody, are too complicated to simply reverse with the process of anti-differentiation. Whatever you think you come up with, if you then go to check that answer by taking the derivative of what you came up with, you will not get right back here to where you started. I'm going to ask you to trust me on that one for now. So how are we going to handle this? We're going to take advantage of the fact that we have a binomial numerator and a monomial denominator. So we're going to split this now. I'll do this once here on this line and then move it down into the integral here of 12 over the square root of z and then minus z over the square root of z, all taken with respect to z. And that's a trick hopefully you guys know that you can do. You can split up any polynomial numerator term by term, but the denominator always remains the same. Now how does that help us? Because now each one of these two fractions can be rewritten in a slightly different way. 12 divided by the square root of z is going to be a 12z to the negative 1/2 power. And then minus, what comes next now? Z divided by the square root of z. Remember, this is z to the first, and this is a z to the 1/2. So let's take this exponent minus this exponent, and we're going to get minus z to the positive 1/2 power, all taken with respect to z. So now we've rewritten each of those terms without a fraction on a single line with z to a power. We can simply reverse the power rule to take the antiderivative of each of these two terms. So here we go. In the first term, we take z, we increase the power by 1, so negative 1/2 plus 1 is now a positive 1/2, and then we take the old coefficient and divide it by the new exponent. Well, dividing by 1/2 is the same as multiplying by 2. That'll give us a 24z to the 1/2. And then for this next term, okay, there's going to be a minus. Here's my base, z. Raise your power by 1. So 1/2 plus 1 is going to get you 3/2 for that power. And then divide your old coefficient, which really was 1, by your new exponent. 1 divided by 3/2 is a 2/3. So that goes there, and there would be this was an indefinite integral, so there's going to be a plus c at the end of all that. Now, that answer right there is perfectly fine. If you were so inclined as to try to write this thing with radicals, which kind of matches the format of the original integrand, you could also write this as 24 times the square root of z, and then a minus 2/3. Okay, and that would be what, guys? It would be the square root of z, and you could put a cube either out here, or you could put the cube underneath the radical right there. Both of those are perfectly fine. Okay, and then there'd be a plus c. Ooh, I thought there'd be a plus c. There we go at the end of all that. So either one of those two answers are perfectly acceptable, and either one of them is going to get you full credit, guys. I'm not saying at this level you have to write it in one way or the other with fractional exponents or with radicals. So both of those will work out fine, and there is our answer to problem number 24.